This is the second part of the very end video for section 49 on connections. So we've got theorem here that says the following. Let G be a connected graph, and let's let E be an edge of that graph, so it's in the edge set. It's going to be a cut edge. Okay, then G minus E has exactly two components. In other words, if E is a cut edge, then removing that cut edge from a connected graph creates exactly two components. It cannot create more. So we want to prove that a cut edge can't be removed and then leave you with three or more components. So a connected graph, remember, has one and only one component. A cut edge is an edge that when you remove it increases the number of components. The point here is that you can't remove a cut edge and go from 1 to 3 or more. It always goes from 1 to 2 when you remove it. So proof. First of all, since G is connected, we know that since E is a cut edge, that G minus E is going to have two or more components, because G has one component. A cut edge is an edge by definition that when you remove it, you increase the number of components. So assume for the sake of contradiction that G minus E has three or more components. So we're skipping over 2 and going to 3. I'm going to show that this leads to a contradiction, and if that leads to a contradiction, then the only possibility is there is exactly 2 components, which is what I'm trying to prove. Okay? So to do that, if it has 3 components, I want to pick 3 vertices out of G that are now in the 3 different components. Okay? So let's let A, B, and C be in different components. Now, if they're in different components, that means there's no path from one to the other once that cut edge E is removed. So we know there does not exist a path from A to B in G minus E, but there is an AB path in G. Of course, that's going to be true for AC and for BC as well. So what I want to show is that I can actually find these paths and thus get a contradiction. Okay? So let's let P be a path that does exist in G. So you can get from A to B in G, but when you remove the edge E from it, you cannot. So that means that P has to go across E. So there is a path from A to B that crosses E. When you remove E, that path is no longer possible. So let's let XY, just for the sake of notation, be that edge. That means P is a path that starts at A, goes across a series of vertices, but crosses the edge XY. Here's the edge XY, and it keeps walking until you get to B. Now, it's a path, so nothing is going to repeat itself, but let's call that P. Notice if we then remove XY, we're claiming there is no path from A to B, because A and B are in different components of G minus E. Also, because C and A are in different components, there is a path from C to A in G, we'll call it Q, that also crosses XY, just because C and A are now in different components once we're in G minus E. So there's 2 possibilities then for Q. Q goes from C to A, just like P went from A to B, and either we're crossing from X to A in the midst of Q, or we're crossing from Y to X. So that looks like this. So either Q is C to cross a series of vertices until you get to X, adjacent to y, adjacent to ... adjacent to b. So c goes to, oh, that's a typo. I should have said b here. Let me fix that. This right here needs to say b. So right here, fix that. Doesn't destroy my proof. Maybe a little different than in the book, but that fixes my problem. And then, as a second possibility, we could go from c tilde ... tilde, or is adjacent to y, is adjacent to x, is adjacent to ... is adjacent to a. Okay? So we'll call that case 1 or case 2. I'm going to show that both cases lead to a contradiction. What I'm going to be able to do is I'm going to find a path from either A to B, B to C, or A to C that never crosses E. Because I've got 3 or more components, I can prove that I can do that. So watch this. Let's say case 1 is the case. That we've got a path from C to B that crosses across E right here. Then I can get from C to X and then from X to A along the path P inverse. So watch this. Case 1, we're going to start at C, follow Q until we get to X, then jump to path P and traverse P inverse from X to A, which means there is a CA path in G minus E. Now there may be some overlap, but the truth is, because of the theorem that says if there's a walk then there's a path, then I have found a path from C to A, but that's a contradiction, since C and A are in different components in G minus E. That's impossible. On the other hand, if case 2 is the case, then what I can do is I can start at C and traverse Q all the way to Y. So start here, traverse till I get to Y. Notice that means I don't have to use edge E, because I don't have to get across E to get to X. So from Y, and then jump across to P, and traverse Y to B. Which means there is a CB path. I can get from C all the way to B without crossing E, which is a contradiction since C and B are in different components. So no matter what the circumstances are, those are both contradictions, which means G minus E can only have 2 components and not more. And that's the end of the proof. So we proved it by contradiction that cutting an edge, that is removing a cut edge from a graph that is connected, creates exactly 2 components. And that's the end of section 49.